Okay? So e to a really big negative number exponent is the same thing as 1 over e to a really big positive number exponent. So 1 over a really big number, so if I think about this, this could be anything. What's 1 over 1,000? That's a really tiny number. 1 over 10,000 is even tinier. 1 over a million is so tiny. It might as well not even exist. 19 times like 0.00000000001 is pretty much just 19. So this e to a really big number, let me say it again. I just totally misspoke. 19, rewind me for a second. 19 times 1 over a really, really, really big number. So 19 times 0.000001. This number is so small, it's basically zero. Maybe I didn't misspeak. Sorry about that. So 19 times a number that's so small, that's basically zero, is basically going to be zero. Okay, so let me restate that one more time. If I confused myself there for a second. I just lost my train of thought. I was thinking ahead. So the last time I said it was correct. So what we have here, sorry, I just had to edit. Okay, everybody. So today we kind of have a two-part video. The first one, we're just going to talk about logistic growth. So you'll have a couple questions to answer on your Google form. And there will be another section of the form with another kind of introduction video to what we're going to be looking at next time. So we're going to start on page 39, logarithmic modeling. And we are going to start by discussing logistic growth functions. Logistic growth functions. So kind of a great example of this, before we look at that next part of your notes, I know you have it in front of you, but this would be like Starbucks coffee franchises opening. So Starbucks stores opening around the Syracuse area, right? It started really slow. So when Starbucks first became popular, like 20 years ago when I was your guys' age, there was only a few of them, and then it kind of took off. It skyrocketed. So it shot up. Everybody wants a Starbucks everywhere. And then eventually there was a Starbucks everywhere. So it leveled out at the end. And it eventually kind of plateaued. And now you see some places closing because of COVID and everything, but that's a different story. But this is an example of a logistic growth function. So it kind of has the characteristics of an exponential curve originally, but then when it hits that maximum point where the environment can't sustain it anymore, it looks a little more like a log function. So it's a really common thing you'll see, especially in population growth, like mice in a cage, deer in our area. The population will explode right away. If you look back at like the history of the population of Syracuse, it explodes for a little while. I think it does for Syracuse, and then eventually it's going to level off because you can't fit any more people here. The environment won't sustain it. So logistic growth functions can be used to model natural growth patterns due to environmental restrictions, environmental factors. So here's our formula. This is not one you need to memorize. I'm going to give you a second to jot that down. And that's what the graph would look like. All right, so notice there's that E there again, which represents kind of the natural continuous growth. And we have a growth rate, we have a time, and we have a couple coefficients. So don't worry too much about what those coefficients are. I have a graph here of what this parent function, not a parent function, but what the function we're going to look at in a second behaves like. So I linked this in the Google form. You can play around with this for a little bit if you want, but these are the coefficients. So notice when A gets bigger, that numerator gets bigger, it kind of controls the maximum value. So when I'm sliding that A value left and right, see what happens here. All right, the B value is the base of our exponential portion. So notice how the B controls kind of how steep the curve is. All right, so how quickly it kind of grows. All right, the R value, where was it? 19, I think. The R value is our growth rate. And same thing, that also is a part of our exponential growth part of this function. Okay, so let's look at the example I have in your notes. So let's just take this made-up problem. In one federal wildlife reserve, the population of bears after T years is modeled by this logistic growth function. And that's what I have up above in the notes. That's what I showed you on the Desmos. So I'm going to give you a few minutes. Pause the video. Just play around a little bit. Think about what the initial population would be. How could you solve for that, either with the graph or algebraically? What would the maximum population be? That's probably pretty clear from the graph. And then what is when is the time frame when the population of bears will be 150? So think about those three questions. We'll look at it graphically and we'll look at it algebraically. So go ahead and pause now. I'll give you a few seconds to think. Well, a few seconds to pause, take a few minutes to think, and then we will talk. Okay, so hopefully you paused. I am back. So when t is 0, when the time is 0, the initial population, that's really just like usual. That's our y-intercept. That's our starting point. So if you went to the graph that I linked and you looked really closely, we're going to see that initial value, when time is 0, the initial value, we could also look at this as a table. The initial value is 15 bears. All right, so let me close that back up. Algebraically, we could do this as well. When t is 0, we're literally just going to plug in 0. So we'll do p of 0, 300 over 1 plus 19 e to the negative 0.3 times 0. Anything times 0 is 0. So we end up with, in my denominator, e to the 0 power. Okay, you with me there? This times 0 is 0. So e to the 0 power. Anything times 0 is 1. So we are left with 300 over 1 plus 19 times e to the 0, which is 1. So we're just left with 300 over 1 plus 19, which is 15 bears. So this population started with 15 bears in their wildlife reserve. So graphically, look at the y-intercept. Algebraically, plug in t for 0. All right. What's the maximum population? How big can this wildlife reserve get? How many bears can it hold sustainably? So we look at the graph. Again, this is pretty straightforward. Whoops, didn't mean to do that. There we go. This maximum is kind of driven by the numerator. So you can see where we were at 300. As this time gets bigger and bigger and bigger, if I scroll to the right of my graph here, it's plateaued. It levels out at 300. So my maximum bear population is 300. And here's why. This is a very kind of a calculus-y idea, and we're going to talk about this towards the end of the year. But if I just think about t being a big number, I could plug in 1,000, I could plug in 100,000. We're not going to really worry about that many years down the road. But if I say just p of a big number, and I just think about plugging a big number into my formula, I have 300 over 1 plus 19 e to the negative 0.3 times a big number. So really what we're doing is we're evaluating what happens when t approaches infinity. So a little word to put in the back of your mind is the word limit. The limit as t approaches infinity. So as t gets bigger and bigger and bigger. That's what we're thinking of right now. So that's calculus. So what I'm going to do here is just kind of like pretend in my head what's happening when t gets really big. So I have 300 over 1 plus 19 e. Now let's think. We have a negative number times a really big positive number. So it doesn't matter what this negative number is. As I plug in, like if I put in 1,000,000 for t or 1,000,000,000 for t or whatever, this is going to turn into a really big negative number. Big negative, we'll call it. So we have e to a very big negative number. So let's say it's e to the negative 1,000th, whatever. E to the negative 1,000th is 1 over e to the positive 1,000th. So what's happening here is a really kind of an important idea when we get into limits. We end up with 1 plus 19. You know what, let me write this differently. We have 1 plus 19 times 1 over e to a really big positive number. What we have here is 19 times 1 over a really big number. So if I think what's 1 over a really big number? 1 over 1,000 is a really small number. 1 over 10,000, 1 over 100,000, 1 over a million. As that number gets bigger, this number gets smaller and smaller and smaller and smaller and smaller and smaller and smaller until it basically becomes 0. And we've talked about this when we discussed asymptotes. 1 over a really gigantic number is a really small number, which is basically, you might as well just think about it as 0. So even if you went to your calculator, you did 19 times 1 over, a really large number. That's basically 19 times 0.00000000000000001. That number is so small, it's really negligible, and it might as well be 0. And that's the idea of what a limit is in calculus. That number is so small, it might as well just be a 0. So going back to our formula, what we have is 300 times 1 plus 19 times a number that's so small, it might as well be 0. So 19 times 0 is 0. So we're just left with 300 for our maximum population. And that matches up with the graph. Okay, so algebraically, that's really what a limit is. It's evaluating what happens when a number gets really, 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 really big. We don't know, we can't plug in infinity, but we can make a really good assumption about what happens. And here, that really good assumption is that this number, 1 over a huge number, is pretty much 0. Okay? So last thing, when will the bear population be 150? This is just a little more practice with our equation solving. So we have 150 is our output. We need to kind of work backwards and figure out what the time is. So we have 1 plus 19 e to the negative 0.3t. And I'm going to pause here, and I'll fill it in while I'm paused, so you guys can work through this on your own. Hopefully we should be feeling good about a question like this. And then when I unpause, you'll see my answer. Okay, so hopefully you paused. If you didn't, just do it now and try this workout. So I plugged in 150 for my output. I need to work backwards to solve for t. So I multiply both sides by the denominator to get rid of that fraction. And instead of distributing here, I'm just going to divide by 150. So if you caught that little kind of nice shortcut there, that saved us a lot of work. So I divided both sides by 150. Subtract 1 from both sides. Divide by 19. And we're about at the point where we can be done. So I have an exponential function with an e base. So I rewrite that as a natural log. Natural log of 1/19 equals negative 0.3t. Divide both sides by the coefficient there. And I get about 9.85 years until we reach that 150 bear mark. All right, so that's the starting point. There's a couple problems that are in the practice set. So I know the next time I'm going to see you, at least this year, I might reuse this video, will be the day before holiday break. So if you want to go ahead and get some of that classwork done, the problems that look like this, you can do it. And that will give you less to do the day before break, and you can get out of class a little earlier. All right, so I'm going to stop this part of the video. And then I do want you to go to the next section of the Google form, and there's another kind of a fun question I'm going to pose to you. All right, good job, guys. I will see you next time. See you. Bye.